Okay, so thank you again. Yeah, so. Okay, shall I start?
Yes, please, you may start now.
Okay, thank you. Okay, so so this is what we were doing yesterday. I just changed this part. So we are starting to do the Whitney density theorem, and then I will get to the spectra of totally non-negative and totally positive matrices. One small announcement is I updated the lecture notes today morning. I think there was, I wrote down, I deleted one word from Sylvester's criteria. So anyway, the updated notes are on the Dropbox folder. Okay, so to get back to this thing, so the theorem stated, the density theorem, that basically totally non-positive matrices are dense and totally non-negative matrices. And so fixed integers Mn, which is the size of the matrices, it need not be square. Fixed P, which is the order of total positivity or total non-negativity, and then the set of totally positive to order T, meaning 1 by 1, 2 by 2, T cross P minors are all positive. Right? That kind of matrices of dimension m cross n is dense in the set of m cross n matrices which are totally non-negative order. Okay, and so the proof, let me quickly recap the proof and then we will continue. And there is a small correction here. So start with any TNP matrix, and we want to approximate it by a sequence of A1, A2, A3, and so on of TPP matrices, which converge to A entry-wise as AK converges to A as K goes to infinity. The way to do this is not just to worry about the M and N, the size and the P, but to also care about the rank of the matrix. So let's start with the matrix A, and it can have rank 0. A can be the 0 matrix. That is clearly totally non-negative of order P. Start with any matrix A, whatever its rank. Okay. Now the construction that we will keep doing again and again is this. Given the sigma, which is some kind of a variance kind of parameter, normally it is 1 over sigma square instead of times sigma. Anyway, so given a positive real number sigma and m bigger equals 1, you define this Gaussian matrix. This sort of taking a principal submatrix of the Gaussian curve. This is a finite m cross n matrix. This is totally positive by the last lecture. And so it's invertible in particular because the m cross n minor, which is the determinant, is strictly positive. And not only that, as sigma goes to infinity, the diagonal entries did not depend on sigma. They were all 1. So they stay as 1. The off-diagonal entries depended on sigma and they go to 0. So this matrix goes to identity matrix. Okay, so we are eventually going to take sigma going to infinity. Not yet. Okay, so now so what I want to do, maybe I should write this down, is I want to construct A1, A2, ... Okay, I want to construct all these guys and these should converge to A. So this is not A1. This is just something in between A and A1. So using this and then doing something more, I will get to A1, the first approximation. Then I will say start from A1 and do the same things that I'm doing here and get to A2. Then do the same things and get to A3. And do the same things and get to A4. And so on. Okay, that is going to be the strategy. Okay, so now how do I get to A1? And once you understand how to get from A to A1, A is like A0. Then you know how to get from AI to AI plus 1, and that's exactly the same construction. So this is how you get from A, which is like A0. You can think of A as like A0. How to get from A0 to A1. And it will be the exact same thing you do to get from A1 to A2, A2 to A3. So the first part of this construction is to define the pre and post multiply by this Gaussian matrix of the correct size. Remember that A was m cross n. So you pre-multiply by the m cross n, post-multiply by n cross n. Fine. Now, as we have seen, because of Cauchy-Binet formula, which we already talked about, this matrix is m cross n. It has rank r because these matrices are invertible, so the rank does not come down. And by Cauchy-Binet, because A was Tn of order P, these two post and pre-multiply still stays Tn of order P. That was one of your tutorial problems or by the previous proposition. Okay, but now here is the point. So far we just talked about Tn, but now we talk about Tp. Right? And so A of sigma, A itself can be the 0 matrix. A of sigma can still be the 0 matrix. matrix. I'm not saying that, right? So A sigma can still be 0. But I'm saying it is totally positive of this order, being R comma P. Why? Because take any size between 1 and this number, you want to prove all determinants of that size of this matrix are strictly positive. Well, so what you do is the following. You look at, so how do you take a minor of this matrix or a submatrix? Take the set of rows of that size, S many rows indexed by J, S many columns indexed by K, and look at the A sigma, this matrix, J cross K, the submatrix, and look at the minor. So my Cauchy-Binet formula, and here I had written something wrong. I said L and M are contained in 1 through this number, but that is false. You can use any rows from 1 through M, any columns from 1 through N. And you would take therefore J cross L, L cross M, and M cross K. We have seen why Cauchy-Binet for 3 matrices gives you this thing. Okay, and now all of these, so here we use the following facts. All of these minors are positive because these are totally positive matrices. How about the minors of A? Well, the point is A is totally non-negative of order P. The size here is less equals P. Therefore, this minor is non-negative every single time. So all of these are non-negative. But also A has rank R, and this size is also less than equals R. So there is at least one R cross R minor which is strictly positive, not just non-negative. And so you're adding up non-negative quantities, and one of them is at least positive, so the full amount is positive. But that is exactly, we started with a minor of this size. So every S cross S minor of A sigma is strictly positive whenever S is less equal to this number, and that proves the claim. Okay, so this is all we did last time. So now let's continue. So now, remember, this is still of order something, and yes, question.
Yeah. Actually, my question is on the claim. You said that A sigma is totally positive of order minimum of R comma P.
Yes.
Can't it be more than that?
It might be, I don't know. But it need not be. For example, I mean, if A is the zero matrix, the zero matrix is indeed this of rank 0. Yes?
Yes.
Here.
Yeah.
If I multiply by these numbers, I still stay at the zero matrix. Nothing changes. And then the zero matrix is indeed totally positive of order 0. It is never, there are no 1 cross 1 positive matrices. Forget higher order matrix. So if A started out by being 0, then this matrix is still 0. And that is just not totally positive of any order. So I do need that.
Okay.
Yeah.
Thank you.
Great. So now we are at, so we started with a totally non-negative matrix of rank R. We got to a totally positive matrix of order min R comma P. Okay, so since this was done last time, I'm going to erase this part because we already saw this last time. I will write the proof here because I want to get to the matrix A bracket 1 by the end of this slide. I don't want to erase that. So I will erase this instead, which was from yesterday, with just that small correction. The correction is also in the notes. Okay. Yeah. Okay, so now the next thing to do, so proof is done. The last lecture. I don't think this is formally a class. Okay, so now let me write down the proof for, so what do you do next? What you do next is you add up, so now you just perturb one entry. I take the top, I guess the top left corner, and I add 1 over sigma over there. Eventually, I'm going to take sigma to infinity. So I'm adding 1 over sigma. As sigma goes to infinity, that will again just not do anything, right? So let me now, so now I think I can define A of 1. I think that's what the next step is. This is all done. Yeah. Finally, here we go. So now define. So remember, I wanted to get from A0 to A1. I should probably keep my A1 in blue. Defined to be A sigma plus 1 over sigma E11. E11, as you know, is the elementary matrix, right? it is 1 in the top left corner and 0 everywhere else. This is all I'm saying. This is literally G sigma M A0. Actually, I should even put a A0 here. Where is the eraser? G sigma N plus 1 over sigma E1. So this is the definition of, so this is the full procedure of how you start from a matrix A0 and get to a matrix A1. And then this is also the full procedure of how you start from A1 and get to matrix A2. Okay, so I can even say, I could even say AK here and AK plus 1. Eventually, that's what we are going to do. Okay, so this is the recursive bit. So I could even tell you that the whole recursion right now. Start from matrix A equals A0 and given AK, define AK plus 1 this way. That is the step. So maybe I'll write this down for me, i.e. start with A equals A0. Let's just use new letters for the actual ones. A equals A0. Given AK, for K bigger equals 0, define AK plus 1 as a 1. Do this for every key. Anyway, that's what the plan is. Okay, but now let us look at what happens to A1. So I know that A0, or if the A of sigma is totally positive of this order. I claim A1 is totally positive of this type. I claim A1 has a rank. The rank of A1 is 1. That's the claim. Let's call this claim 1, claim 2. As far as I believe, it's just the rank. A1 is TNP. It is still TNP. So it's still TNP of rank. Fine. Of rank R plus 1. So why do I want to prove this? Suppose I prove this, right? Then when you do A1 sigma, meaning I do this times A1 times this, that will be TP of order min R plus 1 comma P, and so on. Right? And then we are, I should probably have put in the claim here, right? This is TP of order min R comma P. I just want it to be TP of order, and this is true for all sigma. For all sigma. Everywhere I have to keep saying for all sigma. Bigger than 0. So suppose my R, suppose the rank was already equal to P. Suppose the rank was equal to P. Then I'm already done, right? Because then this is a matrix which is TP of order P for every sigma. So maybe that's actually what I should have first said. Before I did this thing, actually even before I did this. So anyway, let's just insert a footnote. If R is bigger equals P, then A of sigma is TPP for all sigma bigger than 0. So A of 1, A of 2, just take sigma to be positive integers, A of 3 and so on. Look at all these matrices. These are all matrices of the same size, n cross n. They are all totally positive of size P. And as sigma, which is the 1, 2, 3, 4, as sigma goes to infinity, what do these matrices go to? That is the question. As sigma goes to infinity, what does this matrix go to? Anyone?
1.
This matrix, it's a matrix, it can't go to a scalar. So the whole thing together, A was an m cross n matrix, these are square. So the full thing is an m cross n matrix. So the question is, what m cross n matrix does this sequence go to? Or what is the limit? Well, so the point is, whatever matrix multiplication you do, these are finite sized matrices. So taking commute with taking products and sums, because there are only finitely many operations here. With that hint, can you tell me what the answer is? This matrix does not depend on sigma. Only these two matrices depend on sigma. And you know something about what happens as sigma goes to infinity for the two matrices on the left and right. So what does the product of this matrix times this matrix and this matrix go to? It goes back to A, exactly. It goes to the identity times A times identity because of this previous line here. So as sigma goes to infinity, the Gaussian matrices go to the identity. Therefore, pre and post multiplying goes to not doing anything. So A here will just go to A. And so what happens here now? So suppose my rank was already bigger than the order of total positivity I require. Then once I define A of sigma like this, if the rank was already bigger, then A of sigma is already of the desired form. We want a sequence of TPP matrices to converge to A. Well, A sigma is TPP for all sigma. So if you take A1, A2, A3 and so on, that is a sequence of TPP matrices of the correct size, and they converge as sigma goes to infinity to A. And that is exactly what we want to prove. The set of Tn TPP matrices is dense. Every TNP matrix can be approximated by a sequence of TPP matrices. So we would be done. And we would be done. So if R is bigger equals P, if the rank is bigger equals P, then this is it. So all you need to do is you need to keep increasing the rank of this matrix until the point that the rank is equal to P. Once it is equal to P, take that matrix of sigma and that matrix for all higher order sigmas, and then you're done. That's the argument. So now, so the final claim, basically, the final non-trivial claim, then is, okay, sorry. So first I said, so if the rank is P, is same. Therefore, assume from now on that the rank is less than. So assume R is less than. Then we have to figure out a trick to increase the rank by 1 and keep doing this recursively or inductively. And that is exactly the trick here. So this is why all of this part actually goes, sorry, all of this part, what am I doing? All of this part goes inside here. This is where the footnote should have been. Yeah. And I said that at the top of page 6 and I forgot to tell you. That is why I should really closely follow my notes. Yeah, so again, just to start again, we said start with any matrix A, which is PNP of rank R. Define A of sigma in this way, note and call A as A of 0. Notice that A of sigma converges to A. And this is still Mn, the M cross N, it has still rank R, this is still PNP. But now the point is A of sigma is also totally positive of this order. Therefore, if R is bigger equals P, we are done because of this use the higher and higher sigmas. Suppose R is strictly less than P. Then, because we have A of 0, now you define A of 1. Or in fact, more generally, if you have A of K, then you will define A of K plus 1 like this. The claim now is that A of 1 has rank. It is still TNP. It is still TNP. It is still N cross N. But the rank is what changes. This is correct. This is correct. This is not. Sorry, I should have called it A1 is blue. So A of 0 was TNP of rank R and M cross N. A of 1 is M cross N still, of course. It is still TNP, but now the rank has changed. So now I will do exactly the same. If I can prove this theorem, if this I can prove this claim, then I start now with A of 1. I do exactly the same thing. And I get to A of 1 of sigma. That will be totally positive of order min r plus 1 comma p. If r plus 1 is bigger equals p, then we are done by taking A1 of 1, A1 of 2, and so on. If r plus 1 is less than p, then I define A of 2. I claim A of 2 has rank r plus 2. Then I again do the same thing. If that doesn't work, I do A of 3 and keep going. At some point, since the rank keeps increasing, r plus 1, r plus 2, r plus 3, it will keep increasing to a number beyond p. And then I am done. So that is the argument. So basically, I need to prove the claim, and that's about it. And so, okay, so how do you prove the claim? The fact that it is P and P, okay, let's do both of them, right? So take a minor of size S cross S. Where is S? I have deleted it. Oh, sure. Which one do I want to do first? T. Okay, we'll do the T and P part first, I guess. So again, so to prove T and P, so let 1 less equals S less equals P. And let take subsets again, J contained in M, K contained in N, have size S. So we want to look at the minor, J cross K minor or A minor. So, okay, so now let's look at them. So two cases. So case 1, case 2. So what is the difference between A of 1 and A of sigma? See, A of sigma, we already said. Oops. A of sigma. A of sigma was M cross N this thing and is Tn. A of 1, the matrix A of 1 changes this matrix in exactly the top left corner. Right? So can you tell me some easy minors of this of A of 1 that we know to be non-negative? Because I know it for A of sigma. And I have a matrix which I know is P and P, totally non-negative for P, meaning all minors which are small enough are non-negative. I change that matrix in one entry, just one entry. Here. Can you tell me some minors that have to be non-negative because they don't get changed? So what is the condition on J and K for which I can directly check that the minors are not changing and therefore they're non-negative?
Now we can remove that particular column and that row, and then the remaining ones are going to be just like to solve the determinant.
So, and the way to remove it is to suppose 1 does not belong to J or 1 does not belong to K. If 1 doesn't belong to the row, then you are working with different rows, so you avoid the changed entry. If 1 doesn't belong to the column, then you are working with different columns, so you avoid the changed entry. Then, if you look at the minor A1 J cross K, this is exactly the same as the minor A sigma J cross K, because we haven't changed the matrix at all. And this we know by T and P. A of sigma is T and P, therefore the minor is 1. Otherwise, let's say 1 belongs to both. J and to K. Then we have to do some calculation. But the calculation is also easy. Take the matrix, J cross K matrix, and let's say expand along the first row. Right? So then what do you get? What you get is you get the original expansion, but there's an extra factor. Right? If you expand along the first row, the extra factor is this number 1 over sigma times 1 times the cofactor. But the cofactor itself is non-negative because it's a smaller size determinant. The cofactor is non-negative. 1 over sigma is positive, and you are adding, and therefore it's fine. LCM 1 equal to 10, then expanding along the first row or first column. So let's look at determinant of A of 1 j cross k. This is equal to everything else, and everything else is determinant of A of sigma j cross k plus 1 over sigma determinant A of sigma, let's say j minus 1 cross k minus 1. Right? Yes, I'll try to write it slightly bigger. Plus 1 over sigma. This is j cross k, sorry. Determinant of this matrix plus 1 over sigma, determinant A of sigma, j minus 1 cross k minus 1. And this number is non-negative because A sigma is P, and this has size P cross P. This has size P minus 1 cross P minus 1. So of course that minor is also non-negative because A of sigma is non-negative, and 1 over sigma is strictly positive, and therefore this is good. And the whole thing is non-negative. I'll erase this, but yeah. This is the proof that the product, sorry, the updated matrix A of 1 is totally non-negative of order P. Okay, are there any questions? Or why this is true? I can go over it again. And as far as the rank goes, why is the rank?
Yes, you have written S minus 1 plus S minus 1, P minus 1 plus P minus 1.
Oh my God, sorry.
It should be S, I think.
That's right. Okay, very good. Okay. I'm glad someone is paying attention closer than I am. So thank you for that. Yes. This is S minus 1 cross S minus 1. That's right. And this is, of course, S cross S, and S is less equals P. Right. And as far as the rank, okay. So first of all, let's check that the rank. So what was the rank of A? The rank of A was R. The rank of A sigma was R. Okay, that means all R plus 1 cross R plus 1 minus 0. Right? Yes. And then all R plus. Okay, so that's fine. If I have a rank R matrix and I add a rank 1 matrix, then the total rank is less equals R plus 1. That is true. The rank of rank A of sigma equals R implies rank A of 1 less equals R plus 1. That is clear. So I need to just show you there is at least one R plus 1 cross R plus 1 minor that is non-zero. And in fact, I would hope that it is strictly positive. Anyway, it's non-zero. So we want a minor which is non-zero of the size exactly equal to R plus 1. Okay, so let's look at, in fact, let's look at the very first minor. Or now, look at A1, R plus 1. So remember, bracket n is 1 through n. So first R plus 1 rows, first R plus 1 columns. Okay. And A sigma is, and now here is the fun part. Okay, so let's write this down. So again, we write this out exactly the same way. So this is equal to, so it's determinant of it's determinant of A sigma R plus 1 cross R plus 1. Should I do this here? Yeah, fine. Plus 1 over sigma times what? So again, A1 is the matrix where only the top left corner is updated, right? So if I expand along the first row, maybe I should just say that here. Now expanding that A1 R plus 1 cross R plus 1 along the first row. Let's write this up. I will keep this claim because I want to use it. So just coming from here, that A1 R plus 1 cross R plus 1. So again, exactly the same way like this, right? You first forget the extra adjustment factor, and you say this is exactly the full determinant A of sigma R plus 1 cross R plus 1. And this is non-negative because why is this non-negative? Okay, you will see why this is non-negative. Oops. Plus 1 over sigma that of A of sigma R plus 1, let me call it J cross J, where J equals 2 through R plus 1. Right? I remove the first row and first column, that's where I put the 1 over sigma, and the remaining R plus 1, so 2 through R plus 1.
Do you think this determinant A sigma R plus 1 cross R plus 1 is always going to be 0? And then the second term will correspond to the positive part.
Oh, this is rank, this is actually 0, that's right. Forget this thing, it is actually 0. Because the rank of A sigma was R, so therefore this is 0. Now the question therefore is, we want to say the second term is strictly positive. Because as I said, I want that the rank of this matrix we want to prove is R plus 1. So for that, I need a minor that is actually positive of size R plus 1. I claim that this minor already is strictly positive. Well, this determinant was 0, as you said, because rank of A of sigma is R. Correct. So why is this minor positive? The point is the following. J has size R, right? And R, we are assuming here, and this is the whole key. R is strictly less than P. Therefore, A of sigma is totally positive of order R, because R is the minimum, R is less than P. This is a R cross R minor, therefore it is positive. And A of sigma, that A sigma is positive. As A of sigma is TPR. So that is why. One term is 0, the other is strictly positive because of this assumption and this assumption. Sorry, because of this conclusion and this assumption. And therefore we are done. So therefore, indeed, now A of 1 is indeed totally non-negative. That was this part of rank exactly R plus 1, because the rank cannot be more than that. And there is at least one minor which is strictly, but which is non-zero. In fact, it is strictly positive. So that's the end of the proof of the claim. Now again, because you have proved the claim, so now again you can do this thing. Very nice. Now this placement was not bad here. If R plus 1 is bigger equals P, then we are done. Then instead of A of sigma, then we would say that then look at A1 of sigma, meaning pre and post multiply. This will be TPP. And therefore, because this will be TP of order min R plus 1 and P. If R plus 1 is bigger equals P, then min is P. And so this will be TPP. So, so A1 of 1, A1 of 2, A1 of 3, and so on will go to. As sigma goes to infinity, in some sense this goes to A1, but sigma is going to infinity, so even A1 is going to A. And therefore we are done. Right? That's what we are doing. So remember A of 1 is A of sigma plus 1 over sigma times E1. Right? What was A1? A1 is A of sigma plus 1 over sigma E1. As sigma goes to infinity, this is not really correct. If the matrix A1 did not depend on sigma, then these would go to A1. but they depend on sigmas. This is not strictly speaking correct, but anyway, roughly speaking, at least the effect of pre and post multiplying by G sigmas for A of 1 would go away. So at the very least, you would sort of get A1, but A1 itself depends on sigma in this way. So the effect of pre and post multiplying by sigma again here goes away, and 1 over sigma E1 now. But 1 over sigma goes to 0 because sigma is going to infinity. So the whole thing goes to 0. Meaning, so really what I'm saying is, if you look at this thing, if I look at A1 of sigma, this is G is sigma, I'll skip the back. M A1 and then G sigma, right? And then G sigma N. But what was A1? A1 itself was G sigma M, A G sigma N plus 1 over sigma E1. This whole thing was A1. So if I look at A1 of sigma like this, now what happens as sigma goes to infinity? As sigma goes to infinity, this matrix becomes identity. This matrix becomes identity. This matrix becomes identity. This matrix becomes 0, so plus 0. This matrix becomes identity. So it's identity times the middle. So that just goes to the part in the middle. The middle part is identity times A times identity plus 0, which is this thing. So if R plus 1 is bigger equals P, then A1 of sigma is PPP, and then you can do this. A1 of 1, A1 of 2, A1 of 3 goes to A. If R plus 1 is strictly less than P, then you do all this again and get A2. Now look at if R plus 2 is less equals bigger equals P or not, and so on. So continuing inductively, the proof is coming. To obtain A2, A3, and so on. There is the proof. Until, of course, you just need to go until P minus R. And certainly by this point, the rank is exactly equal to P, and therefore you are done. So maybe I should say then A P minus R sigma goes to A as sigma goes to infinity. And they are all PP. Okay, so that is the proof of Whitney's density theory. So it's a recursive inductive procedure, and you have to be very careful in how you handle the ranks and the order of total positivity. But the ultimate procedure to update is very simple. You pre and post multiply by some Gaussian matrix, and you just perturb the top corner. I don't even change the entry that I put. Always the top left corner. And yet keep doing this, you will get to the final. Okay, so are there any questions? And if not, then finally we come to the spectral properties. I should probably say spectra because there are two. Okay. So that's the third and last part of this set of lectures. So I guess you have probably seen Sylvester's criterion for positive semi-definite or positive definite traditionally. Or positive semi-definite matrices. I won't write it down, but I will tell you. The criterion is that a real symmetric, so square matrix is positive definite if and only if all its eigenvalues are positive. No, all its determinants are positive. Right? And positive definite was equivalent to sort of, so there are many definitions of positive definite. One of them is that all the eigenvalues are positive. And another is that the U transpose AU is strictly positive. So yeah, so basically, so one way to state this is that a matrix, a real symmetric matrix, is positive definite. Let's do the semi-definite part later. If and only if let's look at positive definite, let's say has positive eigenvalues. Let's say has all principal minus positive. So this is the conclusion of Sylvester's spectrum. I'm writing it down in the other. All principal minus positive, if and only if all its eigenvalues are positive. Of course, they have to be complex numbers. But I'll just say that they lie in zero infinity. Okay. Now, so what I want to do is the following. I want to say that the same thing holds for totally positive matrices. Okay, so I told you that these are sort of analogous to this, and totally non-negative is analogous to PS. Right? So I want to sort of say that positive definiteness, this kind of condition is analogous. And the analogous part is the fact that we essentially want to say, I want to remove this and just replace it by a square, of course. Square, I can just put the word square here also, that's fine. I want to remove this word and I want to remove this word. If I remove the word principal, then all minus being positive is just totally positive. And we want to claim that the real square matrix indeed is totally positive, will imply at least that all the eigenvalues are positive. To go the converse way, we need a little more statement, which is we need to use the fact that submatrices of totally positive matrices are also positive, and submatrices of principal submatrices of positive definite matrices are positive definite. Okay, so in some sense we have to encode the matrix and all its submatrices as well. So that is the way I have written down the slightly more general theorem in the notes. But I will just prove the small part. Well, I'll prove I'll prove 90% of it, which is the interesting part, which is if you have all minus positive, then all the eigenvalues are positive. So we will prove that part. Okay. So we are going to prove that first. So analogously, we will prove. We now show. Take a square real square matrix, which is totally positive. All its minus, forget the word principal, are positive. Then its eigenvalues are positive. So, you know. Now it's n cross n, it is square. Is totally positive. Not totally positive of order something. Totally positive of order n. Right? Then A has, so it's even stronger than just saying that the eigenvalues are positive. It has positive eigenvalues and there are no repeated ones. Then A has n, the same n, distinct positive eigenvalues. So positive being obviously real. Positive eigenvalues. And the proof is extremely beautiful. The proof is just almost like a magic proof. So it's very weird. So
Excuse me. Yeah, here you have stated that this for TPTN matrices, the celestial criterion, does the result hold only one way? Or it hold backwards as well?
Here the result holds, so I can tell you the full result. So it is that A and all its submatrices that have a. So the full result, maybe I'll tell you the full result here. So let's say I'm given my matrix A. Okay. So maybe I should write this in blue so that I don't. That is just an aside in some sense. So this is a special case of the problem. Special case of theorem. And for this theorem, I can just take A to be rectangle. The following are equivalent. One, all the determinants, all the minors of, so for all submatrices of A, for all square submatrices B of A, all the determinants of B are non-zero, the minors, all minors of B positive. Sorry. This is the definition of total positivity or total non-negativity. Okay. You can even do something more. You can say all minors up to size P cross P. So you can even do T and P or T and P cross P. So this is TP, P or T and P. Or I'll just say TP or TN. Here I'm not using P. But in the theorem, in the notes, I've written the more general. If and only if. So the point is this. The point is this part. So all the determinants are positive or non-negative is fine. All minors are positive. The determinant of a submatrix is still a minus. Right? The point is here. For all square submatrices, same first line. The eigenvalues, so the point is here, you see, here we can only say the eigenvalues of A are positive. That's enough. Here you have to take into account not just the eigenvalues of A, well, in this case it is rectangular, so it doesn't matter, but the eigenvalues of all square submatrices of A simultaneously, together. That and this are equivalent. That is the refinement of that case. But you can also have done the same thing here, because that would not be a problem. So Sylvester's criterion could actually be refined in this exact way, to take the eigenvalues not just of A, but of its square principal submatrices as well. We could have done that. I could have said of A and all its principal submatrices. So the minors are still the minors of submatrices and minors of A, but the eigenvalues of submatrices are not eigenvalues of A. They are interlaced. So there we could still have said that, and that would be fine. Here it actually is necessary. Here it was not. For this thing, all eigenvalues of B are positive, and I think I could instead say non-negative. Okay. Maybe I'll do it the other way. I'll say non-negative, respectively positive, and non-negative, respectively positive and simple. So I do need the simple part as well. That the simple part is here. So distinct is the same as simple. Meaning there are no repeated eigenvalues. Okay. So that's the theorem we will prove, but this is essentially the same theorem. It's very easy. So look, here is why 2 implies 1 is trivial. Why is it trivial? Can anybody tell me? Why is 2 implies 1 obvious? and we will prove 1 implies 2.
Since those eigenvalues are all strictly greater than equal to 0, and therefore the determinant of that is going to be obviously positive, so that will just.
The determinant is going to be?
The determinant of that particular minor or the square submatrix is going to be basically it's the product of the eigenvalues. No? So,
Just the fact that the determinant is the product of eigenvalues. So if all the eigenvalues are non-negative, the determinant is non-negative. If the eigenvalues are positive, forget the simple part, the determinant is positive. That's all. So for 2 implies 1, you don't even need the simple. For 1 implies 2, we will actually prove that it is simple. That's the point. Okay? And the proof, as I said, uses a result. So this uses this idea of compound matrices, which at least in my knowledge, I have actually never seen used anywhere, to my memory at least, other than for the proof of this theorem. But it's a beautiful idea. So here is the idea behind compound matrices, and it's a result called Chronicles theorem. So the proof uses compound matrices. Let us see what these are. So the definition, given integers m n, let's say bigger than, I think I use r in my okay. There is also the Theorem theorem, but I will just state it when we need to use it. M n and r. R bigger equals 1. Here is the rth compound of a matrix and a real. So again, you can take the ring to be, you can take the entries of the matrix to come from the real numbers. You can also take them to be complex, rational, or any unit or commutative, any commutative, not unit, maybe unit as well. You need a unit, any commutative ring with unit. Or R. Okay, so you could take Q, integers, complex number, whatever you want, basically any commutative. And a real matrix A, n cross n. Sorry, The rth compound matrix is defined as follows. So the 0th compound matrix C0 of A is, I think, just 1. Identity 1 cross 1. Okay. The first compound matrix is A itself, m cross n. The second compound matrix consists of, it is an m choose 2 cross n choose 2 matrix, and it consists of the entries therefore are indexed by what? 1 through m choose 2, but that's not very useful. The entries are indexed by pairs of rows and pairs of columns. And what do you put in that particular entry? You take those 2 rows, you take those 2 columns, look at the 2 by 2 submatrix of A for those 2 rows and those 2 columns. I want a scalar out of that submatrix to put in this matrix. That scalar is simply the determinant, the minor. And in general, the rth compound matrix is CR of A belongs to R m choose R cross n choose R. This is the dimension, R to the m choose R cross n choose R. And the entry is what? The entries correspond to, with entries, CR of A, let's call it J cross K, again, is defined to be the determinant of the submatrix J cross K for all J contained in the rows and K contained in the columns of size R. So what happens if R equals 0? That is just convention. M choose 0 cross N choose 0. The empty determinant is defined to be 1. What if R equals 1? Then I take M choose 1. I take one row and I take one column of size 1. Right? I look at the 1 cross 1 matrix and I take the determinant. But what is the determinant of a 1 cross 1 matrix? It is the scalar. Therefore, determinant of a scalar is the scalar itself. What is a 1 cross 1 submatrix of A? It is the entry of A. So the entries of A form a M cross N matrix. That matrix is A itself. So nothing much changes there. But for even for 2 by 2, this changes. So let us look at, for example, let's say A equals 1, 2, 3, 1, 1, 1, and R equals 2. Okay, so this is a 2 cross 3 matrix. So I have to always choose the same 2 rows. That doesn't change. But I can choose the 3 pairs of columns. So C2 of A is a 1 cross, it's 2 choose 2, cross 3 choose 2. And what are the minors? So if I label it as 1, 2, the first 2 columns, the first and the third column, the second and the third column. I'm writing these down in the dictionary order, right? So AB, AC, BC. In the dictionary, they would occur in alphabetical order as AB, AC, and BC. So that's how. What is 1, 2? Well, and the point is the row is only 1 row. So the row has to be just 1, 2. So 1, 2 is 1 minus 2 is minus 1. 1, 3 is 1 minus 3 is minus 2. And 2, 3. 2, 3. Second row and third second column, third column. 2 minus 3 is minus 1. That's the second compound matrix of this of A. Okay. Now it turns out that compound matrices satisfy some very nice properties. For example, C1 of A is A. But interestingly, I can do the following. So suppose I take this matrix. Let me take a second example and you see what happens. Let me take the transpose of this matrix. Okay. Example 1. Example A transpose equals 1, 2, 3, 1, 1, 1. Right? Now I can take the second compound matrix of A transpose. But now this is 3 cross 2. So I get a 3 choose 2 cross 2 choose 2 matrix, which is a 3 cross 1 column matrix. And then entries are again 1, 2, 1, 3, 2, 3, and this is 1. Okay, what is the entries here? It is the first row and the second row of this matrix and the first 2 columns. But that is exactly the first column and second column of this matrix and the first 2 rows. So you can say you get minus 1 here. Same with the 1, 3 corresponds to the 1 and the 3 columns there. So you get minus 2 here and minus 1. But how does that? So how does this compound matrix connect to that compound matrix? Those are not entries, those are the indices, right? Those are the coordinates. So this is exactly equal to the compound matrix of A itself, and then you take the transpose. So either you start with the transpose and then take compound, or take compound and then take the transpose, you get the same answer. So there are some similar very nice basic properties that compound matrices satisfy. For every M cross N and every R and every field or ring or whatever, on all matrices. Let me write down these properties. And then there is a Chronicle theorem. So basic properties, lemma or proposition or whatever I call it. Lemma. Basic properties of compound matrices. Okay, so again, fix a ring, or you can fix real numbers. M, N, bigger equals R, bigger equals 1, or 0. Find zeros. And of course, M is positive and it's positive. I want the actual size of the original matrix to exist. Okay, so here are some things. Okay, another thing I can do is the following. Suppose I took rescale. Suppose I took C. what would happen to the compound matrix here? What would happen to the 2 by 2 minors? If I rescaled every entry in A by some same scalar, what would happen to the 2 by 2 minus?
C square, that is C to the power R in general.
Exactly. So I'm going to write down such basic properties here. So let's see. So CR of C times A is C power R, as you said, and CR for all C scalars. As I said, I'm going to denote scalars in this ring, but you can assume it's rationals or integers or reals or complex numbers, whatever it is, any field. Okay, this one that I just told you, CR of A transpose is equal to CR of A transpose. So just basic properties like this. This is very interesting. What happens if you take CR of identity matrix? Identity N, of course. What do you think will happen? So you have to choose some number of rows of this identity matrix and some number of columns, both of size R. So what would happen if the set of rows you chose, the J, was not equal to the set of columns you chose, K, for the identity matrix or for any diagonal matrix for that matter? What can you say about the determinant of the submatrix? You would either get a row of zeros or a column of zeros. So unless J is equal to K, for any identity matrix, at least, or for any diagonal matrix, you would get 0. So first of all, this is a diagonal matrix. So, but not only that, when J equals K, then what do you get? What is the entry corresponding to J comma J? For it's 1, right? Because you just get identity's principal submatrix. When J equals K, you get a principal submatrix of the identity, that is still the identity. And so basically what I'm saying is when J equal to K, you get 1. When J not equal to K, you get 0. That is, these are the entries of the compound matrix. What is that matrix?
Identity matrix of order NCR.
Perfect. More generally, of course, compound matrices of upper triangular matrices of diagonals are diagonals, but that is even more generally true because compound matrices of upper triangulars are upper triangle and of lower triangulars are lower triangle. So if you intersect the two, then the compound matrices of diagonals have to be diagonal. So lots of nice formulas. Okay, let's see. If rank of A is J, let's say, then the rank of the compound matrix of A, I think this should be R choose J. At least, okay, this is true for some ranks. Anyway, maybe I don't need this rank statement. So this is at least true, you can prove easily for at least for clearly for J equals 0. Also for J equals 1 and for J bigger equals and for J bigger equals R. But for J bigger equals R, I mean, J equals R, this is clear, and for J bigger than R, 0. All we are saying is the matrix is singular. Okay, the next one. What happened to the upper triangle? Very good. Sorry? I don't know what happens if J is less than R. Maybe you can try to calculate it yourself. Or maybe it's there in some book. And as I said, I really never read this, never looked at compound matrices until I looked at this theorem. So I just don't know. Okay. Next, let me see what else. I'm numbering them slightly differently from the notes. Okay. Another one is if the original matrix was square of size n cross n, what can you say about the nth compound matrix? What is the size of the nth compound matrix? It is n choose n cross n choose n.
What size?
It's 1 cross 1, so it's a scalar. What scalar?
Determinant.
Exactly. You have to choose all n rows and all n columns and take the determinant. There is only one possibility. It's the determinant. So I will tell you that. Before that, I will just tell you the fact that I told you just now. If let's say R equals R, let's say, Okay, maybe not. So if A is square or upper triangular, lower triangular, or diagonal, or orthogonal, or something else. Symmetric, or orthogonal. Here R equals R. Then so is the compound matrix. A is square, the compound matrix is square. If A is upper triangular, the compound matrix is upper triangular. For upper triangular, you need square in some sense. If A is square and lower triangular, the compound matrix is square and lower triangular. If A is diagonal, which is the intersection of these two, then so is this. If A is symmetric, then so is this. And the asymmetric part is obvious because if A is symmetric, then this is the compound matrix of A, because A equals A transpose. Therefore, the compound matrix of A equals the compound matrix of A transpose. So that matrix is symmetric. Things like that. So compound matrices preserve a bunch of very simple properties, structural properties of original matrices. Okay, finally now, before I tell you about the compound, the determinant part, let's look at the compound matrix of A times B. Okay, so maybe I'll first do an example. Maybe. Okay, so before I write this down, let us look at the compound matrix of A times B. Okay, and I want the rth compound matrix. Let me look at a subset of rows of A of size R. So okay, maybe I'll make it even better. Let's write down A is m cross n, B is n cross k. Okay, and let's say R is less equals n. Now I take I cross k, a set of rows of size of A of size R and a set of columns of B of size k. Okay. How do you do this? So this is what is this? This is the determinant of AB, I cross k. But we know what this is, right? Does anyone remember what this was supposed to be? Or what was the theorem that told us about this? The Cauchy-Binet formula, right? And so what this was this was equal to summation J contained in N of size K, or size R, and we said determinant of A, I cross J, determinant of B, J cross K. This was exactly the Cauchy-Binet formula. But now look at I and J. These are both subsets of rows and columns of A of size R. Look at J and K. These are subsets of rows and columns of B of size R. Okay, so I can say the following. Therefore, I can say this is the sum of what are determinants of size R of A in terms of compound matrices. These are just the entries of the Rth compound matrix. And therefore, the first term is this, and the second term is exactly this. And we sum up over all possible J's. What is this product? Can you tell me what this product and sum should be thought of as? Remember, don't be fooled by the fact that these are capital letters. These are still indices. These are entries of the compound matrices. So I fix my row and I take all the entries in that row from this compound matrix. I fix my column and I take all the entries in that column and I multiply them one by one and I add them. That is called matrix multiplication. This is how we multiply two matrices. So the fact is the Cauchy-Binet formula is really just saying in terms of compound matrices that the construction is multiplicative. Whenever these things are defined, the compound matrix is multiplied in this nice way. So that's very nice. I will erase this, not erase this, sorry. I'll erase this one. And therefore, now I can say that if A is invertible, the compound matrix of A inverse is precisely the compound matrix of A inverse. You can calculate the inverse of a compound matrix by just taking the inverse of A. Because multiply both sides by the compound matrix of A, and you see that they cancel. Okay, and the final thing. So now for Chronicles theorem. So this is all fine, but here is so now with all this basic lemma, we have Chronicles theorem on compound matrices, and this is what is the key to Untitled theorem to prove total positivity implies eigenvalue positivity. Maybe I should use this blue pen now. So again, fixed integers and no, this time I want a square matrix, and I want a complex matrix. Okay, so let A belongs to C n cross n, have the multi-set of eigenvalues. Meaning I count the eigenvalues with their multiplicities. If 3 of the eigenvalues are 0, I use 0, 0, 0. Lambda 1, lambda 2, lambda n. Okay, let A have this multi-set of eigenvalues. I can calculate exactly the eigenvalues of the compound matrices. The 0th compound matrix is 1 cross 1, so the eigenvalue is 1 for everything else. For 1 less equals r less equals n, the matrix CR of A, compound matrix, has the multi-set of eigenvalues. Or well, okay, maybe I'll state it as I stated it here. What is the size of the compound matrix CR? It is n choose R cross n choose R. So there are so many eigenvalues. The n choose R eigenvalues of the compound matrix are the product J in S. Are literally products of these eigenvalues. It's as simple as that. The products of these eigenvalues are the eigenvalues of the compound matrix, where S runs over all the R element subsets of 1 to n. Where S runs over all n choose R subsets of 1 through n of size R. That is Chronicles theorem. And the proof is like 3 or 4 lines, nothing. That is why. Once you know this basic property, most important, you know this. And you know something for complex numbers called the Jordan canonical form. The point is every square complex matrix, symmetric, Hermitian, anything, can be is conjugate to a matrix in Jordan canonical form. And the diagonal entries in the Jordan canonical form are the eigenvalues. So we know that. And that's all that's going to be used. And before that, let me show you what happens. So before I tell you the proof, let's look at an example of, let me take an example of, let's say, lambda, let's say alpha, beta, gamma. I'll take a 3 by 3 matrix, alpha, beta, gamma, and then I don't care what I have here. So I told you that if A is upper triangular, then the compound matrix is upper triangular, right? Let us look at C2 of A. So this is upper triangular. Therefore, its eigenvalues are what? Its eigenvalues are the diagonal entries, right? Actually, I don't need to do it. Fine, we'll do it. It's exactly the same for n cross n or 3 cross 3. Implies the eigenvalues, E values, is equal to C2 of A, J cross J. For all the J, for J equals 1, 2, 3, and 1, 3. 1, 2, 1, 3, and 2, 3 in alphabetical order. Right? Because it's the entries of the diagonal entries, eigenvalues, sorry, maybe I should have said the following. Since it's upper triangular, the eigenvalues equals the diagonal entries. And the diagonal entries are called J cross J, right? Or J comma J. And the J has to run over two element subsets of the index. So 1, 2, 1, 3, and 2, 3. So what are the diagonal elements? When you have 2 cross 2, then you must take the 2 cross 2 principal minors. That involves, again, principal minors of an upper triangular matrix are upper triangular. And then you must take the determinant. So the determinant is the product of the elements on the diagonal. And the elements on the diagonal of any triangular matrix are the eigenvalues. So you are literally multiplying alpha beta is one of the eigenvalues, then alpha gamma is another eigenvalue, and beta gamma. Because the matrix, if my matrix was triangular, Chronicles theorem is obvious. That's all I'm trying to say. If my matrix is triangular, then Chronicles theorem just said that eigenvalues of the compound matrix are products of eigenvalues of the original matrix. And that is simply because the eigenvalues, because the compound matrix is upper triangular, so its eigenvalues are its diagonal entries. But the diagonal entries are principal minors of some R many rows and the same R many columns. But that principal minor, that principal submatrix is itself upper triangular. So the determinant of that is the product of the diagonal entries, and those diagonal entries are simply eigenvalues. So all I'm saying is this theorem is obvious if the matrix is upper triangular. What if my matrix is not upper triangular? It was any matrix. Then I make it upper triangular using this point, Cauchy-Binet, and the Jordan-Canonical form. So now let me write down the proof in general. But it's like this observation plus the fact that you can do Jordan-Canonical form. That's it. That's the proof of the Chronicle theorem. And then we will get to the theorem we want to prove, that for compound, for totally positive. So far, you see, I have said nothing about real numbers. This can be complex numbers. I have said nothing about, total positivity. There is no total positivity going on. This is some strange construction of building bigger matrices out of determinants or smaller ones. But then it's almost as if this theorem was built, or these facts were built to prove the theorem about total positivity, as you will see in like 5 minutes. So, okay, so Chronicles theorem proof of Chronicle. Write A equals M, J, M inverse, where M is, of course, where M is non-singular. And J is in Jordan-Canonical form. First do this. So in particular, J is upper triangular like this, and its eigenvalues are the diagonal matrix. I don't need to tell you that. Then, because of this Cauchy-Binet formula, the properties from by lemma, if you take the compound matrix of both sides, and this is the compound matrix of M times the compound matrix of J times the compound matrix of M inverse. But the compound matrix of M inverse, as we just said, I just erased it, is the same as the compound matrix of M whole thing inverse. I hope that is clear. I just erased that fact. That since M is invertible, the compound matrices behave well with respect to taking the inverse. So what are the eigenvalues of A? The eigenvalues of A are the diagonal entries of J. What are the eigenvalues of this thing? So here, J is upper triangular because it's in Jordan-Canonical form. Therefore, again by the lemma, the compound matrix is upper triangular. So is CR of J. And the eigenvalues of A are the eigenvalues of A are diagonal entries of this guy. It's okay. Then let's do 3 or 4. One is this observation, eigenvalues of A equals diagonal entries of J. That is because it's the Jordan canonical form theorem. What about the eigenvalues of the compound matrix, which is what we really care about? Well, I think you guys know this. Okay, two matrices are similar.
Similar matrices.
Exactly, right? So then the eigenvalues are the same. Eigenvalues of compound matrix of A equals eigenvalues, first of all, of compound matrix of J. And now I use the fact that the compound matrix of J is upper triangular because J was upper triangular by the basic properties. But then what are the eigenvalues of any triangular matrix? They are the diagonal matrix. This is by using part 1, the diagonal entries. But what are the diagonal entries of any triangular matrix? They are the R-fold products of the diagonal entries of the original matrix. So this is equal to, as I just told you, from the example, maybe I'll call this star. The point was I said this for 2 cross 2, the second compound matrix of a 3 by 3 matrix. But it's exactly the same proof for the rth compound matrix of an n cross n matrix. There is no difference. The same exact let the words used here work. This is R-fold products. So the eigenvalues of a compound triangular matrix are the R-fold products of the elements of the original triangular matrix, which are the eigenvalues. And now finally, I again convert back to saying that by the Jordan canonical form theorem, J and A are, or since J and A are similar, this J can be replaced by B. And that is Chronicles theorem. Okay, so far I have actually done some nice things. These are some beautiful properties, some beautiful observations about compound matrices of elements in any ring, and then for the Chronicles theorem for complex matrices. But now we have to get to the total positivity, right? We have to get to that. So for that, I will need one last theorem then, that is called Perron's theorem. Okay? So to prove our TP, the TP implies eigenvalues are positive. We will need Perron's theorem. Okay. So although this theorem, so what we want to prove is if I am given a real square totally positive matrix, then its eigenvalues are all positive. I want to prove that. But I will actually need this theorem about complex matrices, not just real. And I will need Perron's theorem about positive matrices, but with complex eigenvalues, not just real eigenvalues. Right? So Perron's theorem says, I'll just state the Perron theorem, not the Perron-Frobenius. That is a harder theorem to prove. And again, Perron's theorem is proved in a full proof actually exists in your notes if you want. So again, let's say A is a real square matrix with all entries positive. Let me call it AJK. This is why I like to call J and K, because I is like the square root of -1. We are working with complex numbers. Okay, so then A has a simple eigenvalue. Simple meaning unique group, lambda bigger than 0. So it's also positive, it's a real value. Such that mod mu is strictly less than lambda for all eigenvalues mu not equals lambda. So if you have any other eigenvalue of A, then not only is it not equal to lambda, there is no repeated root. but its modulus, it's a complex number, so it lies in the complex plane. The modulus, the length of that complex, the distance to 0 is strictly less than lambda. So it doesn't even lie on the same circle as lambda. It lies in the interior of that circle. That is Perron's theorem. There is more to it in the thing, but we will only need this much. Okay, so with now all these things, we can now prove the formula we want. Yes. Okay, so there was Chronicles theorem, there was this one. So proof of this theorem. So proof of the TP theorem. I just want to show you that the eigenvalues of any square, real, totally positive matrix are all positive and distinct. Also distinct. They are simple. Okay, so what you do is the following. This is where it's a really genius proof. I don't know who came up with it. I think it was Gartner and Klein, or at least they mentioned it in their 1950s book or paper or something. But anyway, here is the proof of that theorem, of this total positive. Take the look at the first compound matrix of A. So start with it. We have A in Rn is total TP. It's a square totally positive matrix, right? Look at the first compound matrix. What do you get? It is A itself. And all the 1 cross 1 entries of that matrix, all the entries of the first compound matrix are the 1 by 1 minors of A. A is totally positive. So all the entries are positive. So maybe I should have said this is, let's call this as B. Let's call this as C. C is always very, C is going to stand for the compound matrix. So yeah. Right? So then apply Perron's theorem. C equals C1 of A, which is A. Right? The point is, because this is the compound matrix, all its entries are some minors of it. A is totally positive, so all minors are positive, so all entries of this matrix are positive. Then C has a simple eigenvalue. So that means A has a simple eigenvalue. So C has a simple eigenvalue. And okay, which is, let's call it lambda 1. And of course, what we know also is lambda 1 is strictly positive. So in this case, C equal to A. So already we therefore now have that the first that at least one eigenvalue of A is a positive real number. And I'm not okay. And not only that, it's a simple eigenvalue. Okay, so we've proved that at least one eigenvalue of A is positive and simple. I want to prove that all n of them. Of course, okay. Now I look at the second compound matrix of it. Okay, so before that, maybe I should now label that. Let me number the eigenvalues. Okay, so now let lambda 1, lambda 2. Oh, we already knew. We already numbered the eigenvalues. Fine. Let's call this lambda 1. So in fact, we number them. We label the multiset. Renumber or reorder the eigenvalues. Lambda j of A such that the point is A is some real matrix, so it has complex eigenvalues. I want to prove they are real, but I don't know them. So let us look at the modulus, the absolute values of the eigenvalues. These are some non-negative real numbers. I order them such that the real numbers are decreasing, non-negative numbers. And what I know already from the first compound matrix, so this is a strict integral. And not only that, this is equal to lambda 1. Yeah, I don't need to take modulus, it's a positive real number. That's what Perron's theorem says. Okay, so that's so far so good. Now we apply Perron's theorem to the second compound matrix of it. So what do I know again? Because A is totally positive, all 2 by 2 minors are positive. Therefore, all entries of this matrix are positive. So again, the Perron's theorem. This matrix has a positive simple eigenvalue. Okay. That implies C2 of A has a positive simple eigenvalue. What is this eigenvalue? In this case, it was, we called it lambda 1 because that was the biggest in modulus, so it can only be lambda. What about this one? Any guesses? In terms of the lambda i's, can you tell me what it has to be? It has to be the eigenvalue, which is bigger in absolute value than any other choice. So first of all, I don't even know what the eigenvalues are. From them, I want to choose the biggest one.
Lambda 1,
Lambda 1, lambda 2.
Exactly. Now you remember the fact that there was this Chronicle theorem that we proved. That one. And so we actually know the eigenvalues of this guy. The eigenvalues are lambda j times lambda k for j less than 4. These are the set of eigenvalues. And if you take the modulus, then we want the biggest one among them. So what this is saying is the biggest one has to be lambda 1 times lambda 2. So two things there. So therefore this eigenvalue must be lambda 1 times lambda 2. And by Perron's theorem, now you conclude two things. One is that this number is strictly positive. This is not a complex number, it's a positive real number. We also know lambda 1 is a positive real number. So if you divide, then you get lambda 2 is a positive real number. Okay. Must be, phi must be, is in 0 infinity. Moreover, lambda 1, lambda 2 is bigger in modulus than lambda 1, lambda 3. Lambda 1 is bigger in modulus than mod lambda. First of all, I should write this down. This we know because we know it's lambda 1 equals this. We know this is a strict inequality, so we go this. Now here we know that lambda 1, lambda 2, which is also the modulus, of course, is strictly bigger than everything else, every other eigenvalue. That's what this is saying. In particular, it's bigger than the modulus of lambda 2, lambda 3. So what does that give us now? Let's call this equation 1. Let's call this equation 2. Combining 1 and 2, we get two things. One is that lambda, we already knew lambda 1 was in R, and we also knew lambda 1 was bigger than lambda. Right? So here we now get, here also therefore, we should have written two things. Lambda 1 is in 0. We got these two things here. Now we get these two things here. But now that means that lambda 2 is in 0. Because lambda 1 is real, lambda 2 is real, divide. Also, lambda 1, lambda 2 is bigger than lambda 2, lambda 3. But lambda 2 is a strictly positive number, which we just got. So I can cancel it from both sides. Oh, I want not lambda, I want lambda 1. That was the mistake. Lambda 1 is a positive real number. I can cancel it from both sides and I get lambda 2 is bigger than mod lambda 3. Right? Now what do you know? Take the third compound matrix and keep going. Right? So now the third compound matrix, from this, doing the same kind of Perron, this theorem, Perron theorem and Chronicle theorem, you would get lambda 1, lambda 2, lambda 3 is in 0 infinity. And lambda 1, lambda 2, lambda 3 is strictly bigger than what? I want to get lambda 3 bigger than lambda 4. So what should I write here?
Lambda 1, lambda 4.
Lambda 1,
lambda 1, lambda 2, lambda 4.
lambda 2, lambda 4. And then because lambda 1 and lambda 2 are positive, I can cancel them and I get lambda 3 is bigger than mod lambda 4. From here, because lambda 1 and lambda 2 are positive, I cancel and say lambda 3 is positive and keep. And so just magically, this is Chronicle. So Chronicle was really set up to use total positivity because for total positive matrices, compound matrices have only minors as entries, so they're all strictly positive entries. And then I can use Perron's theorem for a matrix having strictly positive entries to get the eigenvalues. So it's as if these two are almost tailor-made for this fact, and so every step you get, eventually you get all lambda j are positive and lambda 1 is strictly bigger than lambda 2 is strictly bigger than lambda 3 and so on. And that was the theorem we wanted to do. So yeah, so you just note down some basic algebraic properties of how to choose rows and columns correctly for conical. Then you note that Jordan canonical form, the arcs, it's not, I'm not saying the Jordan canonical form of the compound matrix is the compound matrix of the Jordan canonical form, but at least it's similar to it. And therefore the eigenvalues. But then the eigenvalues are just k-fold products of the diagonal entries, i.e. of the original eigenvalues. And now you can use that in Theorem to just recursively, inductively get that the first eigenvalue is positive, then the second one is positive, then the third one is positive, and the first is bigger than the second, now the second is bigger than the third, third is bigger than the fourth. And together that gives you the proof of the theorem. Okay, so that's about it. Sorry, I went a little over time. Sorry, I started.
Excuse me.
Questions?
Yeah. Well, we have studied that these positive